guys, Nicole here with another tutorial. Tonight we're going to be talking about floating point formats. So this will be the last one for a little bit because I am going to be moving after this. So there's a lot of moving parts. I won't have my green screen and my equipment for a little bit. So more to come eventually, I promise. But what a better way to spend a Saturday night, right? I know you guys are probably like, what? So that's what we're going to talk about tonight is floating point formats. So we're talking about what is floating point format. We're going to talk about how to create a number. We're going to take a fractional decimal number, decimal fraction, from that value to its floating point binary format. We're going to convert it to hex, and then we're going to go back. So it should be a pretty fun night. So if you've ever heard the term before, you may have seen it in Blender. Sometimes you'll see you can put your values in float. You might be like, what does that actually mean? So you're in the right spot tonight. So now this is going to be, we're talking about single point 32-bit floating point format. There is double precision. There's also quadruple precision, which is 128-bit, and then there's also octuplet precision, which is 256-bit precision. So we're only going to be covering 32-bit precision for tonight's tutorial. So, but if you can do this one, then you can do the other ones as well. No worries. All right, so let's go ahead and get started. So for this tutorial, you can see we have our 32 bits. Now you might be looking at this and going, why all the highlights in our little bit here? So well, I did this to kind of make it a little bit easier to see things. So for this green bit here, this is going to be our sign bit. So we're going to start with what is stuff in the 32-bit field. So it's, in this case, we're going to do a 32-bit floating point format single precision value, right? So hence why we have 32 bits here. So we have one sign bit, which is over here in green. Then we have this like peach color over here, and that's our exponent field. So that's our exponent. Now this will make more sense here in a minute, I promise, in a little bit. And then the pinkish color that you see at the end here, I'll just put this over like this. That is what we call, there's a couple terms for it. So one is mantissa. You might see that in books. So I'm going to write that up here, mantissa. Also known as fractional bits. So that's an easier way to think of this. So these are our fractional bits. So the reason it's called floating point format is it gives us the ability to float the decimal point or move the decimal point. The first time I heard that, I was like, wait, how does that work exactly? So basically, it's a system that allows us to represent positive and negative numbers. So we're going to sign bit on the most infinite side, like we've been talking about all along. But we're also going to be able to basically a floating point number allows us to represent a really large value really precisely using scientific notation. So that's what this is going to be about. So let's go ahead and jump into it. So for this number today, we're gonna convert negative number 390.625, and that's base 10 decimal. So we're gonna convert this to binary. So basically, the first thing I'm gonna do here is I'm gonna convert this to binary. Now, just like everything else, if it's a positive number, the sign bit positive. So if it's positive, then the sign bit will be a 0. And if it's negative, I'm going to leave this here too so you guys have it. Then if it's negative, then the sign bit will be 1. Okay, so in this case, I'm going to start by putting a 1 in the box over here. So I'm going to put a 1 there, just so we're on the same page. So that represents the negative value. So the easiest way to start here is we're going to start by breaking these values down. So I'm going to start with the whole number first, then I'm going to break down the .625. So we do the 390 just like any binary number. Decimal number to binary. So I'm going to start by making my least infinite side, just like we've done in all the tutorials so far. Most infinite side over here, just like this. And then we're going to do something like this. So I'm going to start with 1, 2, and each time I write this number, I'm asking myself, can this number fit in the 390? And as soon as I get to a point where I can stop, I'm going to stop. So 4, 8, 16, 32, 64, 128. I'm trying to write straight here too. 256 today, so we got to go up to 256. And then the next number up would be 512, which is not going to fit in the 390. So anything beyond 256 is going to be too big So it'll just be zeros behind here anyway. So we could literally stop where we're at this point. So now I'm going to start at my 256, and I ask myself, can this number fit into 390? In this case, it can. So we're going to put a binary 1 here, and I'm going to do a little bit of math over here. So 390, we're going to subtract 256 from 390 like so. And that's going to give me, so we got 4, we got 3, and 1. So 134. So now, again, I'm going to ask myself, can 128 fit into 134? In this case, it can. So we're going to put a 1 there. I'm going to subtract 128 from it, just like this. That leaves me with this number here. So 14. That's going to give us 6, I believe. Yep, so 6. 64 cannot go into 6, so we're going to put a 0 there. 32 cannot go into 6, nor can 16 or 8. 4 can go into 6, so we're going to put a 1 there. We're going to subtract 4 from 6. Gives us 2 left over. 2 can go into itself, so we're going to say 1 under the 2. Subtract the 2 like so. Leaves us with 0. 1 cannot go into 0, so we're going to 0 this field out. And this becomes our binary number at this point. So I'm going to clean this up here. So that's the number. So that number there is 390. So that's our 390. So I'm going to leave this up here like this. I'm going to put this in binary, just like that there. So that's 390. So this is 390 in binary. So yeah. So now I did this in another tutorial, but again, this will be a refresher. So now we're going to convert this 0.65. So I'm going to take 0.625, and to convert this to a binary number, what we're going to do is we're going to multiply by 2, and our goal is to get to, we stop at 1.0. Now this kind of makes sense because we stop when we get to 1.0 because that's a whole number. So as soon as we hit this exact whole number of 1.0, we basically stop. So at that point, so that's our goal. So every time we multiply, we're going to multiply this number by 2. So I'm going to say 0.65 times 2, like this. So I'll put this up. So 5 times 2 is 10. Carry the 1. 2 times 2 is 4. Plus 1 is 5. 6 times 2 is 12. Carry the 1. 0 times 2 is 0, plus 1 is 1. We're going to move the decimal place 3 places to the left, and that gives us 1.25. So essentially, this becomes our first binary number for 0.6. So for the other half, so for the, I'm going to write it down here. So for the 0.625, if I could write that, our first number is going to be a 1. So we got a 1 there. So now I'm going to get rid of that. So now I'm going to rewrite this. I'm going to say, now we're going to take 0. Because basically think of it like we've taken this 1 and we're using it over here. So now that's gone. So now we got 0.25. So we're just going to focus on the fractional value. So 0.250 times 2. I guess I could have left the 0 off there, but that's okay. 0 times 2 is 0. 5 times 2 is 10. Carry the 1. 2 times 2 is 4. Plus 1 is 5. 0 times 2 is 0, and we're going to move the decimal 3 places to the left. Bring it over here. So in this case, we get our next binary bit is going to be this 0 here, and we're left with 0.5. So we're going to put a 0 down here. We're left with 0.5. So I'm going to make some room over here. So 0.5 times 2. 5 times 2 is 10. Carry the 1. 0 times 2 is 0, plus 1 is 1. Move the decimal place 1 place to the left. And you can see now we can stop because we are at 1. So this will be our last bit. So here we have the 1, that's our last bit. Right there like that. And we stop because we're at 1.0 essentially. So that's our stopping point. So pretty cool, right? At least I think it's cool. This is how I spend my Saturdays. Doing binary. So now what I'm going to do here, just for organization purposes, I'm going to rewrite this number. So this number here equates to this. So we got, let's do this. So we got 1, 1. We have 4 zeros, like this. And then we have 1, 1, 0. And think of it like this. Think of it, we have a decimal point here, and then 1, 0, 1, just like that. So this is how we represent 390.625 in binary, right? Just like that right there. So now I'm going to get rid of all this stuff down here. I'm sure we'll probably do it again here in a little bit. So just like that. All right, so hopefully this is all making sense. So now the next thing we have to do is we gotta move this decimal point. So now the way floating point format is designed to work is the rule is we're gonna move it either left or right, but the rule is we're gonna move it to a position where there's only one binary one to the left position. So in this case, we have a whole bunch of ones on the left, and if we go to the left, we're making a bigger number. You can see we're going left over here. So we're gonna move over. In this case, I'm gonna go like this. I'm gonna go, and I might just color code this here. Let's make this like we'll make it red. so we're gonna go from this point here. We're gonna go 1, 2, 3, 4, 5, 6, 7, 8 positions to the left. So we're gonna move it 8 positions to the left. So we're gonna have this exponent of, so the exponent field is gonna be a positive 8. Think of it like that, right? So now where does this come in? So to get our exponent field, it's going to be based off the number 127. So we're always going to subtract. When we're actually reading this value later, we're going to take our number and we're going to subtract 127 from it. We always do this. Now the reason for this is similar to offset binary. So essentially it's an 8-bit field. So this represents the middle point essentially. So you can think of it like 0 through 126 is going to be all of your negative exponents, and 128 through 255 will be all your positives. So that's where that number actually comes from. So what we do in this case is we're going to take, to figure out this exponent field, I'm going to take 127, and you're always going to do this. And in this case, because it's positive, we're going to add it to it. So if this was a negative exponent, like if we moved it to the right, we'd subtract it from 127. We get a lower number, which would be on the left of the 127 in the scale. So what I'm going to do is I'm going to add this, and that should give us, so here we got, we should have, let's see here, 8, that's 15, that should be 15, right there. So we'll carry the 1, that's going to be 3, 135. So here we got 135 base 10. And then what I do is I convert this to a decimal number. So I told you guys I'd be doing the scale again. 1, 2, 4, 8. I won't bore you guys with the, so we'll go through it kind of quicker this time. I know you guys are probably bored of this by now. 64, 128. And I don't have to go any bigger because 256 is too big. So 128 does go into 135. Over here we're going to say 135, subtract 128 from it. Leaves us with, let's see here, 15. That's going to be 7 right there. So we're left with 7. So I'm going to do this a little bit quicker. So we got 0, 0, 0, 0. 4 plus 2 plus 1 is 7. So I can literally 1 all these out. Now, the more you do binary numbers, the easier this will get. You will start to see these things. And so that's the only reason I know that so quick. So this number here is our exponent. So at this point, we've figured out our sign bit. And that number right there that you see goes into this box right here. So we have 1. Oops. Let me just get rid of that dot. I don't want that to look like a decimal point. I'm just going to rewrite that. OCD here, guys. OCD. So we're going to do 1. We're going to do 4 zeros. So 1, 2, 3, 4, and then triple 1. 1, 2, 3. And realistically, if I had less than 8 bits, I would just pad it to the most significant side. But in this case, it works perfect for us, right? So now you might be thinking, and I know this is probably happening, what happens to this value right here? Like what exactly happens to that? Well, because it's scientific notation that we're talking about here, we assume, basically it's assumed. So this bit is an assumed bit. So when we go to recreate this bit, we're going to assume that that bit is there. So when we're going to, so we basically don't include this bit. It's because scientific notation always has 1 times something. So this is where this is assumed. So so basically, if we have like scientific notation, you always have a 1. Like that's the assumed bit essentially. So we don't include it in the actual values, but when we undo the process, it's assumed that when we go to actually read these fractional bits, there's always a 1 to the left of all these bits later on. Okay, so this will make sense when I undo this process later. So we'll see that again. But just want to put that out there. That's what that is. So this bit there is assumed. That's always, it's there. We're not including it right now, but we will come back to that, I promise. All right. So at this point we have our exponent field, and what we do is we include the rest of the bits. So in this case, over here we're going to write the remainder of the bits. So we're going to say 1 here. These are our fractional bits that are left over. So we got 0. We got 4 zeros. 1, 2, 3, 4. 2, 3, 4. And then we get 1, 1, 0. Now remember, we moved the decimal point over here, so this isn't actually here anymore. So now we're going to do 1, 0, 1 here, and then we're going to fill this with zeros rather. So we're going to go 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that is our number. So now if I wanted to, I could convert this over to hex. So essentially, now what I do in this case is I'll go something like this. I'll actually break these into like little sections like this. 4-bit nibbles, we'll say, like something like this. Now this is going to get pretty messy, but so for now. So we got 4 bits there. I like to do this because it's easier to see everything in hex. You'll see that in the computer world, in programming and things like that. Everything's in hex because it's a little bit easier to see things. Let's see, and now I know it's 32 bits because I got an even number of 4-bit sections. So 1100, that's going to be C in hex for 12. This one 0011 is 3. So here we have 3. 1100 is C in hex. 0011, that's going to be 3. And then 0101 is 5. Here we have all zeros. These are the easy ones. 0, 0, and 0. So basically what we have, 39.0.625 negative, if that's a negative number, is equivalent to 0x C3 5 000. So how cool is that? So that is the floating point format of that number right there. So now it is a lot of work to get to this point. So if you're looking at this and you're going like, wow, because I know I was the first time I saw this, you're not alone. So computers do this much quicker and much more efficiently than what a human can do it. So, but pretty cool though, right? Pretty cool. At least I think it's cool. So now what I'm going to show you next is I'm going to show you how to take this number back to the, like, how do we read that number now? Like, so we've converted a decimal number, a fractional decimal value, over to floating point format, 32-bit floating point format, and this is using the IEEE standard is what this is. So now how do we get back? Like how do we read that number and go back the opposite way? So we have C3 5 000, C3 5 000. So I'm going to rewrite that up here. So oops, if I could get my pen working here. So C3 5 000, and that is in hex. So I could do a base 16 if I'd like, right there. So that's our number, right there. Okay, so what we're gonna do here is I'm just gonna rewrite this number. So what we'll start with is we know we have C for the first 4 bits. So C is gonna be 1100. That's 12. 3 is gonna be 0011. C is gonna be 1100. 3 is going to be 0011, just like that. And then 5 is going to be 0101. Then the last 3 are easy, so it's all zeros. So 0, 0, 0, 0, 0, 0, 0, 0. I'm getting tired, guys. 0, 0, 0, 0. I can feel it. It's late. I'm getting like, okay, sleepy. Now I realize I've been doing this for a while, so you can also do it this way. You can also put numbers above this if it's easier. So this is going to be for hex 1, 2, 4, 8 is how I'm figuring this out. So 8 plus 4 is 12, and C equals 12. So you could do it that way too. So you could just do 1, 2, 4, 8 over the tops of each of these if it makes it easier. So just wanted to put that out there. So nothing wrong with that. So what does this tell us? So again, this is our sign bit. So this is our sign bit over here. So we know we have a negative number. So this tells us it's negative. So we have a negative number because we have a 1 there, right? We're then going to read these bits here. So we're just going to reread these bits in the peach bits. So I'm going to rewrite them down here. So we have 1, we have 4 zeros, 2, 3, 4, 111. So we're going to rewrite these. Again, least in a bit over here, most in a bit on this side over here. We got 1, 2, 4, 8, 16, 32, 64, and 128, which is this one right here. Ugh, I ran out of room here. There you go. Okay, that's that one right there. So basically what we have is 128 plus 4 plus 2 plus 1, which should give us, and it's still good to check this kind of stuff. So 8 plus 2 is 10, plus 4 is 14, plus 1 is 15. So we go to 5, carry the 1, 2 plus 1 is 3, bring the 1 down, and that gives us 135 in decimal. So what we do here is we take our number, which is 135, in this case here, and then we subtract 127 from it. And when we do that, that gets us our exponent field. So that gives us the exponent. So 135 minus 127 gives us 2 here. 15, that's going to give us 8. So there's our exponent 8. So basically what that now tells, so my exponent in this case is equivalent to 8, positive 8. So we'll get back to that now at this point. So you can see we're just kind of going back through the process, right? So now, how do we get the rest of our number? So all I do now is I do this. So I'm gonna remember I said before about the 1 bit. So the one that's assumed for our fractional bits. Remember these. This is our exponent over here. That's our exponent. I'm gonna rewrite this here. And these are the fractional bits, also known as mantissa. So that's our mantissa. Or fractional bits. I think I spelled that wrong, but you guys get the idea. Fraction bits. So we get all our fraction bits over there. So basically, what I'm going to do is I'm going to rewrite my number. So we know our exponent is 8. We know it's positive 8. So we're going to move the decimal place 8 places to the right because it's positive at this point. So what I'm going to do is I'm going to rewrite my number. So I'm going to say 1. Because remember, there's an assumed 1 in scientific notation. This is where this comes from. And then I'm going to say decimal, right? And then I'm going to rewrite this number. That's all we do. So we're going to say 1, and then 4 zeros. 1, 2, 3, 4. 1, 1, 0, 1. 1, 1, 0, 1. 1, 1, 0, 1. 0, 1. And then we have a whole bunch of zeros after that. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 zeros. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Really, I don't have to write those. But now the more where this comes in, you can see in this example here, we didn't actually use all these fractional bits. So the more of these bits you use, the higher the precision. Think of it like if you worked at a machine shop. The further you go to the right in your fractional bits, the more precision you get. And it's the same thing here. So if we had a really precise number and we use more of these bits, we can get very precise. The further you go to the right, the closer, the more accuracy we get. So this is where this comes from. So and single precision, 23 fractional bits is a lot. That's still going to give us a lot of precision. The reason I use the number with the 0.65 is for simplicity, but for this tutorial, but you could go all the way up to 23 bits there and get really high precision. So now what we do is we move this decimal place. And again, I'll color code this so we can see a little bit better. So we're going to move it 8 places to the right. So we got 1, 2, 3, 4, 5, 6, 7, and 8. So the decimal point is going to come over to this point right here. So I'm going to rewrite it like that. So what we get is this. You can see where we're going with this. So I'm going to rewrite this number now. So we get 1, 1, we get 4 zeros. 1, 1, 0. And then we get our decimal point, and then 1, 0, 1. And I'm just going to stop at the 1 there. We don't actually need all the zeros. And that's our binary number. And then we just convert this back over. So I'm going to start with the whole number. So we're going to start with that first. So we'll say, so we'll go 1, 2, 4, 8, 16, 32, 64, 128, and then 256. There we go. So I'm going to add all the values that have a 1 underneath. So in this case, I'll do it over on this side just to give us room. So 256 plus 128 plus 4 plus 2. 4 and 2. So we add all these numbers up here. So let's add all these up. So we get 10. So 8 plus 2 is 10. Plus 6 is 16. Plus 4 is 20. So we got a 0 here. Bring the 2 around. So 5 plus 4 is 9. 2 plus 1 is 3. So like magic, this is the 390. So there we got our 390 back. Now how do we get the fractional bits back? So this is the part I want to show. And I mentioned this in another tutorial how this works. So this will be good practice to see this again. So I'm going to rewrite this 101 over here. So remember, these are the fractional bits that are left over at the end. So 101 over here. This is equivalent to this. It's equivalent to saying 2 to the negative 1, 2 to the negative 2, and then 2 to the negative 3. Now what does that mean? Well, anytime we have a negative exponent, that means what we have to do, we can actually, to get this to an actual positive value, we just make the reciprocal of it. So what I mean by that is 2 to the negative 1 is equivalent to 1 over 2 to the power 1. This number here is equivalent to 1 over 2 to the power 2. And this number is equivalent to 1 over 2 to the power of 3. And if we do a little bit of math here, you can see that, so I'll do it over on this side again just to give us room. So 1 over 2 to the power 1 is 2. So 1 divided by 2 gives us this. So this is going to give us 0. Bring the 1 down. Let's bring this down like this. So 2 goes into 10 5 times, which is this. That gives us 0. So basically this number here is equivalent to this much, 0.5. That's for the 1. All right, and then we're going to do the next number over. Now obviously if you had a calculator, this would be a lot faster. So just showing the process here. 1 to the power of 2 squared is going to be, 2 squared gives us 1, that's going to be 1 over 4, 1/4. So 1 divided by 4 gives us this. One a decimal point there, bring a 0 down. 2 times 4 gives us 8. I'm running out of room here. 2, I think I have just enough room here. 0, bring the 0 down. 4 goes out 25 times, and then 0's out. So we're left with 0.25. So this number here equates to, it's worth 0.25 right there, which is 1/4. So this is half of 100. This is a quarter. And then the last number we're going to do over here is 1 over 2 to the third power. 2 to the third power is 2 times 2 is 4. 4 times 2 is 8. So this is going to be 1/8 is what that's going to be. So we're going to do 1 over 8. So 1 divided by 8 gives us this. So 1 divided by 8. 8 can't go into 1. So we're going to 0 that out. Bring the 1 down. We'll make a decimal number there. 0. Bring my decimal point up here so I can see it this time. 2. So 8. That's going to be 1. 1 times 8 is 8. Told you I was tired. Told you guys I was tired. All right, 0. Bring the 0 down. This is going to go twice. 2 times 8 is 16, leaving 4 behind. Last number is a 0. And you can see that brings us to 0.125. 5 times 8 is 40, leaving 0. So you can see this last number is 0.125. So now the further you go to the right, this is what we were talking about before. So the further we go to the right and the more fractional bits we add, the more precision we get from these actual fractional bits, these values. So that's where that precision comes from. And the further you go to the right, the closer to the actual number you get. So, but the more bits you use, the more space we take up in file space. So it's kind of a trade-off when it comes to this kind of stuff. All right, so now what do? So to actually get back to our actual decimal number, or fractional number, we're going to add the ones that have 1 underneath. So in this case, we're going to add the 0.5. And I'm going to add 2 zeros here just to make it a little bit easier to see things. And then we're not going to add the 0.25 because there's a 0 here, but we're going to add the 0.125. So we're going to add the 0.125. And when I do that, like magic, We got, that's going to be 5, 2, and 6. Look at that. How cool is that? So that gets us back to the 0.625 that we saw earlier. So basically we went back the opposite way. We know it's a negative number, so I'm going to put my negative sign, and that is how we get back to the original number. So base 10. And you can actually check this. You can actually Google floating point format, IEEE, that's the standard. And there are calculators where you can actually check your work and actually put all this stuff in, and you'd get the same exact reaction. So pretty cool. So that is floating point format in a nutshell. So I hope you found this tutorial interesting as I did. I know it's Saturday night. Nothing like doing floating point format on a Saturday night. So keep practicing. Again, don't let this stuff scare you either. Like I said, usually computers do this for you, but it is handy to kind of know what is floating point format and why is it called that, and why does it give us this high degrees of precision. So I hope you enjoyed the tutorial, and I will see you on the next one eventually. So like I said, it'll probably be a while until I do another tutorial, maybe a little bit, but hope you find these tutorials helpful, and see you on the next one. Happy Saturday, guys. Happy Saturday.